interrupt you with questions?
Yes, I'm happy with that.
Okay. So it's a pleasure to have Professor Vivian here today to give us a talk. Professor Vivian got her bachelor's in 2003 at the State University of Londrina, her master's at Phys in 2005, and her PhD in 2008 at USP São Paulo, sorry. She did two postdocs after that, one from 2008 to 2009 at USP São Carlos, and then one from 2010 to 2012 at University of Freiburg in Germany. And since 2013, she has been a professor at UNESP. Now she's an assistant professor. And today she's going to talk to us about entanglement as a problem of metal-insulator transitions in the Mott-Anderson regime. So Professor Vivian, it is a pleasure to have you here. Thank you very much for having accepted our invitation, and the microphone is yours.
Okay, so thank you very much, George and Edson. Also, Crisia, for suggesting my name. Let me just move here to my talk. As you know, now I cannot see you, so if you have any question, I suggest you just open the microphone and interrupt me. It's fine by me. So, and I'm really happy to bring these results to discuss here with you. They are quite recent yet, and it's a part of our research. Here I'm just showing our group. There is a bit weird that we are in a chemistry institute, but actually there is now this Department of Engineering and Physics and Mathematics. And this is our group at the moment. I think you can see my mouse. No. No, even me, I don't see my mouse, so I'm sorry for that. And well, so what we are doing at the moment, we are using several approaches like dense functional theory, DMRG, machine learning calculations to treat many body problems in general. And some of the specific properties we are most interested on are entanglement, exotic superfluidity, mainly FFLO state, and in general quantum phase transitions. But these results that I've brought to this talk today were actually performed by my former PhD student, Guilherme Canella, who has finished last year, and also in collaboration with Crisia, who is in the audience, Zavadzis, our collaborator, right? So here I prepared the outline of the talk. So mainly I will begin with the description of what is this disorder situation we consider within Hubbard chains. And then after that, I will briefly describe what kind of entanglement we are calculating in these chains, and also how we have been connected this quantity, this quantum information property, to quantum phase transitions. Then I will just give you an idea of our approaches, so our methodology, which is essentially DFET with several approximations, dense function approximations, and after that, the results and conclusions. So here we consider one-dimensional Hubbard chains with this Hamiltonian at zero temperature. So here, essentially what we allow for the hopping of particles in this chain, but only next neighbor hopping, and also on-site interaction. So it's the most simple Hubbard description. We could in principle extend this Hubbard by including extra terms in this Hamiltonian. But for now, we have just the next neighbor energy, this first term. Then second, we have the interaction, on-site interactions only. So only when the particles are at the same site, they interact with this strength U. And this third term, which is this VI, will be used to describe our disorder here. There are several ways we could define this VI to describe disorder, several possible landscapes that we could simulate in principle. But in all our results, we have used a specific way to define this disorder, which is what I'm explaining right now. So what we have, we define a certain number of disorder of impurities with a certain intensity V. So all the impurities that I put in my chain have the same V, and I choose a certain number of impurities. That defines what is here in the third line in the left side, the concentration of the system. So essentially we have this number LV of impurity, and that is a part of the total chain with size L. So that gives me the concentration. In all our case, we have 100 sites in the chain, L is equal to 100. And the point is that the V is well known. So we know exactly what is the intensity of the impurity, the strength VI of this impurity. And they are all the same for all the impurities that I put there in the chain. What is random here is only where the impurities are really placed. So the distribution of impurities along the chain is random. Okay, so that's how we are define the disorder in this system. And this V might be, of course, attractive or repulsive, and we vary this concentration, we vary the intensity of V, but the main features is that what is really random here is the position where these impurities take place. Okay. Well, and then we are really interested on the two main mechanisms in this case that may lead the system from a metallic state to an insulator. This is the MIT, right? So the metal to insulator transition. One of them is the interaction, the Coulomb interaction, which is the Mott metal insulator transition. In which this, in the Hubbard, what we have is the short range interaction. So it only happens when we have the density n equal to 1, so at half filling. Now, considering the disorder, we know from Anderson localization that these randomly distributed impurities cause some coherent backscattering and localize the system in several ways. So what the regime that I'm calling here Mott-Anderson regime is simply the regime where we have both interaction and a certain disorder in V as defined just before. Okay. And then we will look at this physics by analyzing entanglement. So in a very simple way, a bipartite entanglement, let's say between two subsystems A and B, is mathematically defined by this equation. That means that you cannot factorize the substates of systems A and B, right? And where is my, oh, here. So we know that if these pieces A and B share this entanglement, they share a certain degree of entanglement. That means if we perform a measurement in one of them, say A, this will affect immediately the other system, the state of the other system B. And the point is that A and B may be almost anything in the system. And depending on what is this A and B, which are these subsystems A and B, you have a different type of entanglement. So it could be two particles, it could be 2 degrees of freedom of a single particle as charge and spin. And among other possibilities, it could be also spatial regions of your system. And this last type of entanglement is the type that I'm interested in here. So it will be a piece of the chain entangled to the remaining part of the chain. So it's a kind of spatial entanglement. And so the point is that it's not a matter it's not only a matter if you have or do not have entanglement in your system. So it's not just with or without entanglement, but also the system may may present different degrees of entanglement. So it's very important to quantify this degree of entanglement. And so now bring this general definition of entanglement to the Hubbard chain. What we use here, I choose a single site A, as it appears in the figure, and then I calculate the entanglement between this site and the remaining chains. Notice that this is pretty much dependent on the site I have chosen to be the subsystem A. So what we do, we vary this choice and take an average to the entire chain. So we calculate the entanglement between each site and the remaining chain, the L-1 sites, and we vary this specific choice and take the average. So, and well, when we have this bipartite entanglement, just one site and the remaining, and it's in the ground state, we can define properly the measure of entanglement, and that is it can be quantified, for example, by the linear entropy, which is given here by this equation. So one trace of rho square, where this rho is the reduced density matrix of that site. So we can here write this equation as it's written here, where these W's are simply the occupation probabilities of that site. So we have for the Hubbard, for this single band Hubbard model, we have only 4 possible states: doubly occupied, empty, or with spin up and spin down. And these probabilities, these occupation probabilities, will then be combined in this formula to give the linear entropy. So this will give me the degree of entanglement of the average single site entanglement. Okay. Well, then how this has been used in the Hubbard model? Here I'm showing just some of our results, previous results, where we explore different transitions. So it has nothing to do with the metal-insulator transition. It's in superfluid regimes. The last article, the last paper is also in disordered chains, but still in a very different regime, where we have attractive interaction in the Hubbard model and so. But the point is that even in very distinct regimes, in very distinct systems, the signature that has been associated to a quantum phase transition in this type of average single site entanglement is a non-monotonicity with the parameter which drives the transition. So we see here these 2 examples that I won't give you the details right now, but in the x-axis, we have the parameter which defines or drives the system through a transition. And what we see as an impact of this transition, this quantum phase transition in the entanglement, is a non-monotonic behavior with this parameter. Now, concerning the methods we have used here, essentially most of the results I have here are via DFT within a LDA approach for the exchange correlation energy, as given here, where we use as input of the LDA a fully numerical solution of the Libivu equations. And then what we do, we choose for each specific interaction density concentration V for each set of parameters. We consider 100 samples of randomly distributed impurities in that chain, and then take an average of that to get rid of the specific. Yes.
May I ask a question?
Sure.
I'm a bit confused by the use of DF2 because you have a model Hamiltonian, you don't have a material Hamiltonian.
Yes. So it's a very good question. Actually, indeed, it's more common that you do ab initio DFT it's but we can also apply DFT for the for models if you have density functional for that model.
Okay, okay. I didn't know that. Okay.
Yes. So, but it's a very good question, because it's not so common to apply DFT for models. I mean, it's common, but in the sense that compared to the ab initio DFT calculations, it's really less used.
Okay.
But it's the same fashion. So essentially, you have, what we do is, compared to ab initio, we have already simplified the problem. So we have a next step. So before in ab initio calculation, we would use the full description of the system, and then on top of that, try to approach with dense functional theory and approximations for the exchange correlation energy of these particles and so on. Now, what we do with the Hubbard, first, we simplify a lot the ab initio problem to a system which has a restricted interaction, restricted hoping. So we do an extra approximation, which is the Hubbard. And then on top of the Hubbard, if we know the dense functionals, then we can do DFT too. So what means apply DFT in this sense means essentially solve the Coulomb scheme with some approximated dense functional for the exchange correlation energy, and get the energy and density profiles similar to what we do in the ab initio, but in a system that is much more simplified already.
Okay.
I hope I have answered.
Thank you. Sure. Thanks.
Yeah. So then this is what we get from the DFT with LDA for the Hubbard. We essentially get the energy and density profile. Then to really calculate the linear entropy, we also have a dense functional for the linear entropy, which has been proposed many years ago already. And we use this dense functional tool to simplify the problem of finding, instead of using the exact linear entropy, we have also this approximation here. And then when we do this approximation, we also do DFT on top of this second block of results. So we do DFT, get energy and density profile. With these DFT results, we plug in this approach, this approximated formula for the linear entropy, and we do an LDA on top of that to consider the inhomogeneous situation of the disorder case. So we have an LDA also for the linear entropy. So it's really a set of approaches and approximations. So we have the approximation of the Hubbard itself, then we have the approximation of the exchange correlation energy, which we do via LDA, and then we also have this approximated analytical but approximated linear entropy, and on top of that we put another LDA to cover the fact that the chain is inhomogeneous. But the point is that when we compare the results of all the set of parameters to DMRG, we see a very fair result, of very good results. So, so it's really a set of approaches and approximations to calculate this quantity, this linear entropy, so this average single site entanglement. And as we see here, as a function of the average density, even with this with several details that I will explain just in a moment, we see that all this approach is reliable when compared to DMRG results. Okay, so then now I would like to start to discuss our results, and I like to start by showing only the Mott, so without the disorder, and then only the Anderson localization without the interaction, to see what we get there, which pictures we have, which features we see in the entanglement, to then put all them together afterwards. Okay, so start with the Mott case. So here the system is not disordered. not disordered. So we don't have disorder at these curves. And we look at this property, this entanglement, as a function of the density. We start with u equal to 0, which is the blue curve. And we see that the system up to n equal to 1 is essentially monotonic. We have, of course, for larger densities than 1, we have the particle-hole symmetry, but up to there, the blue curve is completely monotonic, showing that for u equal to 0, no interaction at all, we don't see any quant-phase transition there, and our entropy remains then monotonic. But when we turn on the interaction, the orange curve is still almost the same, but our results, I think I didn't mention, but there was in the previous slide, that our linear entropy is not so good for very weak interaction. And here it seems to be the case. We are not seeing anything when we turn on the interaction for u equal to 1. But the point is that for stronger interaction, we start to see that precisely where it is expected, the Mott is expected to appear, which is n equal to 1, the entanglement decreases and then becomes non-monotonic even between 0 and 1, right? So among this regime, we see the non-monotonicity. And the interesting thing, so it has this minima there, and this minimum is becoming, it's a local minimum, but it's becoming even with lower entanglement when we increase interaction. But it saturates in a specific entanglement value, which is given by 0.5 when you do this u going to infinite. Okay. And the reason for that, so this decrease of entanglement is the signature that at that particular density we have frozen. We have frozen these degrees of freedom of these particles for that specific density, which is precisely the localization we expected when we are in the half-filling, the Hubbard model for repulsive interactions, okay? But the point is that it saturates in a finite value of entanglement. So it means that although it's frozen, the degrees of freedom of the chain is frozen, but it's not completely frozen. And the reason for that is because just the charge degrees of freedom are frozen out. And while we still have spin degrees of freedom that makes the entanglement different from 0. Okay, and so we call this fact as and also to compare to the Anderson case, we call this state at n equal to 1 as a partially localized state, essentially that has a finite value for entanglement, saturates at a finite value. Now, when we look at the Anderson case, so now I don't have any interaction. Instead, I just have those impurities randomly placed with a certain concentration, and I vary then this the density and also adjust the intensity of those impurities. What we see is that the blue curve is again monotonic, so there's no interaction, no disorder. Entanglement has no one-phase transition. And when we turn on the interaction, the disorder strength, and here I have chosen the attractive case, but when we turn on, we see in general that the orange curve goes down in general for any density. So this decrease of entanglement for any density suggests that in general there is a kind of localization already. Okay, but when we increase even more the intensity of this disorder strength for more or less larger than 3 times c, we see that it starts to appear a local minimum which was similar to the Mott, but that depends on the concentration. So here it's at n equal to 1, 2, but it's just because I have chosen this concentration to be 50%. Okay, so if I choose a different concentrations, this Anderson critical density where this minimum appears, it changes proportionally. So here is the equation, how this NC, this critical density where I see this minimum entanglement occurs, it's proportional to the concentration.
Vivian, I have another question, sorry.
So, thank you.
This average density is the density, the electronic density or the density of impurities?
This is the electronic density, so the filling. Okay. Yes.
So you are at a fixed density of impurities and you are varying the electronic density. Okay.
Yes. So this concentration C is more related to a kind of impurity density, because this gives me how much impurities I have compared to the total to the total chain, how much sites I have with impurities, the C, and they are connected. So the electronic density for which I see this minimum at the entanglement depends on the concentration of impurities.
Okay.
But the main difference here in comparison to the Mott is that if I increase further the disorder, I can really reach zero entanglement. So that means I'm really localizing the system. In the Anderson case, what we then use to differentiate from the Mott case is that we have a fully localized state when V goes to infinity, and in that specific critical density. Okay, so here to summarize, looking at the Anderson, we see that the entanglement decrease for any density and any V, but when V is larger than, more or less larger than 3, we do have a specific critical density, electronic density, that makes the system completely localized if we increase this V. Okay, and then we reach zero entanglement. So now the question is, what happened when we put these two things together, interaction and disorder? So here is, I will depict the figure with you to follow all the features. So the first thing we notice, so here I have the blue curve, which is only U equal to 5, so we have only interaction. And we do have the Mott minimum at n equal to 1. We see the minimum related to Mott as before. Then I include in the orange curve some disorder, but with a very low potential, so weak disorder. 25% of impurities in the chain, but with intensity -1. So what we see is that if this impurity is not strong enough, only -1, we don't see the Anderson minimum expected to this specific concentration I'm using. That should be at 0.5. There is nothing there. I'm marking with this dashed line. There should be a minimum, but for very low disorder strength, we don't see the minimum as the previous result. But we also see that the overall trend of the blue curve is remaining. So almost no difference if you have just impurities with a very low intensity. Okay. Now, when we increase the potential of these impurities, increase the disorder intensity, we start to see several features. The first that I would like to mention is the fact that the minimum related to the full Anderson localization appears precisely at the same critical density as before, meaning that the fact that we have interaction doesn't change the critical density, doesn't change the density for which we reach the full localization. Okay, it doesn't change. But the presence of interaction makes the entanglement a little bit higher than before. So it's a minimum in the entanglement, but the value of this minimum is stronger than before. That means, and we have explained this feature, but due to the competition between interaction and disorder strength, that makes more difficult to reach that full localization. That means I need a stronger disorder potential to reach the full localization marked by zero entanglement. Okay, so now if we increase further, we see exactly this behavior, which are these other two curves, the red and the brown curve. We see that for -20, then we have reached the zero entanglement, the full Anderson localization. So the critical position, or the critical density is the same, where I can find full localization. However, I need a stronger disorder potential because of the presence of interaction and because of their competition. Okay, but when I was constructing this six curves for you, there was also another feature appearing here in the right side of the figure, which is the fact that what was the minimum related to the Mott was displaced by some factor, which is given here, right? So the present, now that's the effect of the disorder on the Mott minimum. So we see that the presence of disorder displays the density where I can see the Mott physics. So, and that's very nice to explore, because we found, of course, where was this critical density precisely. It's given by this formula. So the displacement is 1 plus, it goes from 1 to 1 plus C over 100. When we have a repulsive disorder, instead of displace to the right, we displace it to the left. So it's a very beautiful symmetry between plus V and minus V. I will show you in the next slide. But the point is that this displacement is related to the fact that when we have this very strong attractive disorder, we populate these impurity sites, and then the chain the overall chain remains with a kind of smaller effective density, because part of the density is plugged in these attractive sites, very strong attractive sites. So then to reach n equal to 1, where I would expect to see this Mott physics, I need a stronger density, more than n equal to 1, to compensate this fact that I'm losing some particles for these attractive sites, and have an effective density n equal to 1. So in a sense, so it's an effective density phenomena, and in a sense, it is like only, it means that the chain is not entirely at n equal to 1, as the non-disordered case, Mott case. Instead, I have just a part of my chain at n equal to 1. And this is already enough to see a localization in a part of the chains. So in some sites, I have this localization. And it also decreases entanglement in comparison to the orange case. So it displays to the right, and it also has a smaller entanglement because now I have the two features there. So I have the Anderson localization at the impurity sites, and I have this effective phenomena with n equal to 1 at some piece of the chain, some parts of the chain. And then another, the last feature of this figure is very, very smooth, which is this two here in the left, which we are calling Mott-like phenomena, because it also comes from an effective density phenomena. But now the situation is that we are having n equal to 1 at the attractive sites, at the sites with impurities. So there are two features related to a part of your chain that has reached the n equal to 1 filling, and therefore has a decreasing of the entanglement there. But this is very smaller effect compared to the other. And it's also only present when we have these two features, interaction V. There was nothing like that in the only interacting system without disorder, and nothing like that in the system with disorder without interaction. So it's really a new feature, quite small, but it's also there, and we could find exactly which was the critical density that happens to guarantee that it was an effective density phenomena when we have pieces of the chain with n equal to 1. Okay. Well, so then plugging this critical density in a table, we have this structure here. So if we have no disorder, the first line is for no disorder, only interaction, we see that the entanglement has a local minimum at this critical density n equal to 1. So we already know that it was at n equal to 1, of course, but now it's the feature that we can see in the entanglement. Then for the Anderson, without interaction, which is the second line, we see the critical concentration for which we find even a zero entanglement, so a fully localized state, so at this critical density. And when we have the tree case, we had three minima in the curve. One, the first, which is related to the Mott, but it's displaced for some value that depends on the concentration of the impurities. The second, critical density that appears there, which is the same as before from Anderson, but now it disorder potential to reach the full localization. And the third, which is very the new stuff here, but quite subtle, because it's also associated to effective density equal to 1. And the nice thing is that we can, so this table here was depicted for attractive disorder, and we can go to the repulsive disorder by just doing a particle Hall transformation. That means pick these 5 critical densities and simply replace by 2 minus these critical densities when going from minus V to plus V, as we also show in this figure. All the features are there with this nice symmetry. Okay. Then we also look at this particular behavior of the minima when we vary the concentration instead only of the density. Okay, so here I'm looking at the same quantities, these linear entropies, everything as a function of the concentration, and we were more interested in how the interplay between U and V might define whether we have all those features or only pieces of them. And that's exactly what we see in this figure. We see that for some regimes of interaction compared to the disorder, so that's the regime for U smaller than V over 2, we just see the Anderson minimum, the fully localized, full localization at the Anderson regime. So that means the curve blue, which makes U much smaller than V. Here, for this figure, V equal to 5. So the blue curve and the orange more or less satisfy this condition. The orange not much already, but as soon as whenever U is smaller than V over 2, we only see the Anderson localization minimum. That is different from what I've showed before. There, I always had all the minimum, right? So now we have an interplay where some of the features appear or not, depending on how U and V are related to each other. Now, we see that if U is larger than V, then only the Mott-like minimum appears, which is the smallest feature here, this smallest minimum, which represents those not fully localized state, the partially localized one. But when we have here U larger than 10 and V larger than U, so for this combination, very strong interaction, very strong disorder, then we do have the 2 minimum, okay, which was the previous case too. So strong interaction is strong disorder. And we have the two minima, which are in this second graphic that I'm showing, are this I don't know, green curve, gray, and the pink, and also this brown one. So for V larger than 10, we see this fact, okay, that we have the two minima related to the two features at the same system. Then we also analyzed for for small chains, we also considered the temperature effects for these two minima, full Anderson localization and the Mott-like, and how the minima behaves when we increase the temperature. And here is the results. We see that, of course, the two minima, which represents this metal-insulator transitions, the two minima start to disappear when we increase temperature, but the full Anderson localization survives for higher temperatures than the Mott-like one, which was already also a more smooth feature of this system. And we also have considered the presence of magnetization in the chains. Up to here, all my chains with spin up and down, so no magnetization, zero magnetization. And in these graphics, the first graphic that I'm showing to you, where we plug in some internal magnetization, that means I have a difference between particles with spin up and down. And so here is essentially three cases. And the main feature we see here is that while before I could see only one single full Anderson localization minimum in the entanglement, which is also the black curve, and we have a balanced system, same amount of particles with spin up and down. When I have polarization, when I have a difference between the population of spins, we see that appears two minima instead of only one. Okay, and we found precisely where these minima should appear, and they are pretty much the same, but happening in a different way for each species, since they are different in number. So it also associates to a specific critical concentration that makes that species, spin species, frozen in the impurity sites and completely frozen to make entanglement goes to zero. But the point is that in contrast to the non-polarized case, non-magnetized system, we now never reach the full localization. So entanglement decrease, we have the minimum, they are specific for each species, but pretty much the same in a similar fashion that before. However, even if I make this V very strong, the magnetized case never reached the fully localized state. That means that it still remains, what is also reasonable, it still remains spin degrees of freedom in the system. So it saturates in a finite value of entanglement for the three magnetized cases I'm showing to you, in contrast to the non-magnetized case, which is the black curve that I'm just seeing here. And with that, I come to my conclusions. I think I was on time. So here are the main conclusions of these two works, quite completely related works, right? So first, I have shown to you that the interaction impacts the full localization by requiring a stronger disorder intensity to get this fully localized state. Then the disorder affects the Mott localization by displacing its critical density where it happens. Then we also find this exclusive Mott-like phenomenon, which is related to this interplay between U and V. And comparing these two cases, the fully Anderson localization and the Mott-like, we see that there are regimes where only one of them appears. So for U smaller than V over 2, only see the full Anderson localization. For U larger than V, only Mott-like localization. And only when we have very strong U with V larger than U, we see both features in the entanglement. We also show that the full Anderson localization is more persists for higher temperatures than the Mott-like one, and that the magnetization prevents the full Anderson localization to occur. We always reach a partially localized state when the system is magnetic. With that, I thank you very much.
Thank you, Vivian, for this very nice talk. So we are open to questions. I'm sure that Edison has a question, or more than one.
I don't know if I should just go back to you, if you turn on the camera.
Yeah. So, no questions, Edison?
Yes, I do.
Yeah.
Actually, thank you, Vivian, for a nice talk. So most of my questions I had made already some time ago, and I had some trouble with my connection. I think only this was on my problem. Was it okay for you, George?
Well, there were some glitches, but they were very fast.
Yeah, I think my connection is pretty bad.
Okay.
So, but I still was wondering if that was not your calculation, but was imagining if you start, you don't do time evolution, right? So I was imagining if you start with a particular initial state, and what happened in so we know that in the Anderson localization regime, you would have non-thermalization probably for some initial state. But when we have both interaction and disorder, what would you expect?
So it's a good question. What we do, we also evolve the system for these temperature results that I've showed to you. And maybe Krisia, who has performed these calculations, could comment. I don't know if she's still in the audience. But
she's gone.
She's gone. I'm not sure if she, when doing these calculations, this is for smaller chains, and she evolves this, but I'm not sure if she had problem to go. I'm talking about these figures here. Let me just come back to the temperature, right? So what we know from this result that I was not. How can I change this? I don't know. Okay. So I was not so fair when I showed this figure, because there is a particular specific feature here, that is the fact that we still use this linear entropy, but this linear entropy is not well defined as an entanglement measure when we have temperature. So, but the idea here was try, okay, perhaps it's not quantifying precisely the entanglement alone, because the point is that when we have the thermal fluctuations, we also have we cannot guarantee that the linear entropy is quantifying the entanglement itself. It's quantifying the purity of the subsystem, but not necessarily the entanglement anymore, that non-factorized equation. So our idea was, okay, although we do know that's not precisely a measure for the entanglement anymore, in part, we could try, the minimum should disappear smoothly with this quantity, which is not anymore the entanglement measure, and so. And then we evolved the system to get this, but I'm not sure if these instabilities, these things that you mentioned, how it could affect, in fact, the calculation. I really don't know. I should
time evolution here. You use time-dependent DMRG, right?
That's I'm not sure. I think it's not DMRG. It's a very small chain for this case. I think it's just exact diagonalization. We have here in this number here we have 8 sites. So it's a very small chain.
Yes, it can be done. Yes, that's right. It can be diagonalized. Okay, thank you.
You're welcome.
Any more questions? I have a question if anyone. Yeah. I am really surprised with what I learned today, that PFT can treat model Hamiltonians, that people would do that. And even more surprised that I saw one of your slides saying that for U much larger than T, the results are more reliable, which is the opposite of what you get when you apply the FT to ab initio calculation. If U is the size of T, you are already in a dangerous place, and if U is much larger than T, you are wasting your time because it won't give you.
No, it's a very important question. Let me make it clearer what I mean there. So let me so here, right? So you are talking about this functional becomes more precise at U, much stronger, right? So in general, as in the ab initio DFT for the Hubbard, we also see that in general the LDA might be suffer some problems with strong interaction. It also happens for the Hubbard in general. So the same trend that we expected, that this approach via DFT with LDA, in principle, it becomes more complicated if you have a strongly interacting system, in principle. But now, this statement here is really concerning the way we have proposed this approximation for the linear entropy. So in there, so it's nothing to do with the LDA that we perform. Instead, it's just because we have used the exact information of the Hubbard model when U goes to infinity to depict, to construct this precisely formula for this approach here. So that's why. So it's nothing to do, it's not the same problem that we typically see in DFT with LDA. Instead, it's more related to the way we have constructed this guy. And this guy, we have used a lot of information to the strong attractive limit to the when U goes to infinity. We really use the exact results from Libby-Rule integrals for U going to infinity n equal to 1. And that's why the approach becomes better when we have strong interactions.
Okay. It is more clear. Okay, thank you.
But also in this sense, I also would like to comment that this LDA that we perform in both scenarios, they are not exactly approximating the interaction. In principle, if we have a very good functional that describes the interaction, the DFT calculation should give a nice result. Because what we do with the LDA is essentially approximating the spatial inhomogeneity. So it's not really a certain approximation to the interaction, but more an approximation of how I treat the fact that my system is inhomogeneous. I do that via this spatial localized, this local approach that I can consider locally as a homogeneous system. But if I have a very good functional that describe properly the interaction, this LDA will not make it worse, you know, because it's attacking a different problem.
Okay, I have another question. If there are no other questions, you are talking, although you didn't mention that or didn't emphasize that, you are looking at quantum phase transition, right?
Yeah, sorry, George, I could not really listen to you well in this question now.
You are looking at quantum phase transitions, right?
Yes,
Yeah.
yes.
And there is this whole. I come from the corporate community in the that was in the mid 90s to beginning of to the mid 2005. In 10 years, I was doing corporate, and there was all this discussion that you could explain the strange metal that appears right above the superconducting transition by saying that there was a quantum phase transition under the dome of the superconducting dome. And what you are varying is the concentration of holes in the Hubbard model in 2D. So it's something that is, it's a quantum phase, no, it was proposed that it was a quantum phase transition. And so when you raise the temperature, all the signs of the quantum phase transition would appear at a finite temperature and would give origin to this strange metal that was what was condensating into the superconducting state. Did you look for anything like that? Any signs of this kind of physics in your calculation?
No, not yet. No, I don't think so. So for these results I've present to you, we really only have the metal. We have a metal in first of all, and then with disorder or with the combination of density and repulsive interaction, we go to an insulator. So we never look at the superfluid regime in these results.
Well, but what at least the people who were the advocates of the quantum phase transition, they would say that this is a general feature of any quantum phase transition. That when you go up in temperature, you will still see the properties of the quantum phase transition appearing.
Okay.
So they have that drawing that is, you have one phase here, the other here, meeting at t equals 0. So you have one phase here, and when you go up in temperature, this region here between the two phases would be a strange phase that is some complicated thing that would justify the existence of, in the case of the cuprates, would justify the existence of this strange metal that nobody understands until today. So it's a general feature. It doesn't require that you have a superconductor.
I see. Then now I understood your question. Yes, we did not compare that with temperature. We only have that figure where we still see some signature of a kind of localization. And that might be related to this strange phase, but it's quite complicated to properly define this quantum phase when we have temperature. How much of that feature even might measure. Since it's not entanglement anymore, I cannot really separate how much of the feature that I'm seeing, minimum that I'm still seeing, is related to a quantum feature, a quantum phase transition, or different phase, strange phase or so, or is just related to temperature fluctuations, the classical fluctuations, right?
Okay, thank you.
Okay.
Let's see, nobody raised her hand. So if Edson doesn't have any more questions, I already asked more than I usually do. We thank the speaker again for a very, very nice talk, very didactic. I am learning more and more about entanglement, and that was very helpful.
Okay, thank you very much for the invitation. Hope to see you next events.
I'm gonna be writing to you to ask for